तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
We have been discussing so far the methods of analysis of continuous time systems, where the variable can take values as continuous functions of time. You recall that we mentioned in the introductory part of this lecture series that in contrast to continuous time signals, we have what are called discrete time signals. These signals take values at discrete points along the x-axis, that is representing the independent variable, and usually this independent variable is time when we talk about dynamics of systems. And so a discrete time signal has values defined at discrete points along time, discrete points of time. Very often, and this is by and large the case that we will be considering, these discrete points are evenly spaced in time. Therefore, the interval between one sample of the signal and the next sample is constant. We can call this capital T. This is also called the sampling period. So in a discrete time signal, we have a sequence of values of the signal which are occurring at regular intervals, and this can be represented by means of a figure like this. Like this. So if this is a discrete time signal, we can call it f and t. This is t, 2t, 3t, 4t, 5t, etc. And the amplitude of the signal at different sampling instants is indicated by these vertical lines, and this is what we call a discrete time signal. In contrast, as you know, a continuous time signal f of t is defined for every value of time t. That is the distinction between these two. So in a discrete time signal, we have the function described at discrete points of time, and usually it can be, of course, negative t also in general. So we have these signal values normally occurring at regular points, at regularly spaced points along the time axis. We usually normalize t to be 1, and we can represent these signals as fn itself. So this is the notation which we will normally adopt, unless the sampling period is to be other than 1 second. We take this to be 1 second, and therefore we can write this as fn. Another notation for this is fn. So this is more compact. Sometimes we use f as a function of n and r f suffix n. In contrast to the continuous time signal, where t is the independent variable here the independent variable is n. So n is the independent variable. So the values of the independent variable will have jumps. It will be 1, 2, 3, 4 and so on. Integral values of the independent variable is what the values that we consider at which this FFNT is described. Such discrete time signals occur sometimes naturally. For example, if you are talking about the attendance in a class, the first class, second class, third class and so forth, there is no point in having saying 1.5 classes or 2.5 classes, so it occurs naturally in such a context. Similarly, if you are talking about the yearly outturn of graduates from a particular university, then again each year you have a certain number and therefore there is no meaning attached to a fractional part of an year. Suppose we have a long ladder network in which we are interested to know the voltage at different nodes. So this can be thought of again as a discrete time system where the voltage is a function of the node number. Now even here, even though the voltage is a function of a discrete node number, the independent variable is not time in this case, but it is the position of the node. Even in this case, we loosely refer to as a discrete time system, even though the independent variable does not have anything to do with time. Another example may be if you are interested in finding out or specifying the number of centuries scored by Sachin Tendulkar in each calendar year. So you have the number of centuries, that is the dependent variable, and the calendar year is the independent variable. So you are taking the value of a particular signal at discrete points of time now, which are spaced apart by 1 year. All these are examples of discrete time signals which come naturally. On the other hand, you may have a situation where we have a continuous function of time, f of t, and you sample this at discrete points of time and generate from that f of nt, where you take stock of this continuous variable at discrete points of time. So this is a sampled version of a continuous time signal. So very often we have to deal with such discrete time signals which arise from a continuous time signal by sampling process. For example, you might like to record the temperature, daily temperature readings at 8 o'clock in the morning. The temperature is a continuous signal, but you are sampling it at discrete points of time at every day at 8 o'clock. So this is a sampled version. Similarly, we want to send several pieces of information over a telemetry channel, pressure, temperature, humidity and so on and so forth. You sample these signals at discrete points of time and send all these one after another on the same channel. So here again you have a sampled version of a continuous time signal. In sample data control systems, this is a common phenomenon. You sample a quantity and then use that information to control that quantity. In speech signal, digital signal processing, a speech signal is sampled and then the sampled version is a discrete time signal. So we have basically two different types of situations where discrete time signals are encountered. One where they occur naturally as the first category we talked about, and secondly where they are generated from a continuous time signal by taking the samples at discrete points of time. So the term sample is probably applicable to the second category of signals. However, in a loose manner of speaking, even when they occur naturally as in the first category, like the attendance in classes and so on, we refer to the particular value at a given point of time also as a sample because it's quite convenient to refer to it in that manner. Now it is also possible for us to, just like the independent variable is quantized, it can take only these definite values, it's possible for us to also specify that the amplitude of the signals also can occupy one of some discrete levels. So instead of varying continuously in the vertical direction, we may also specify that the amplitude, the value of the signal at any point must take one of some specified levels. In such a case, this is called a digital signal. For example, if you have got a sample version of a continuous signal obtained and then this is digitized through analog digital converter. Depending upon the number of bits you use in the conversion, the output will correspond to a value which again takes discrete values. So that is called a digital signal. A digital signal is again a discrete time signal, but the amplitude of the signal is confined to certain well-defined limits. As far as our course is concerned, we will allow the signal amplitude to vary continuously. That means these signal values can vary continuously in the vertical direction. We are only discretizing it in the as far as the independent variable is concerned. So we are not talking about digital signals, we call them discrete time signals. So that is the difference between discrete time signal and digital signal. The thing to keep in mind is that the independent variable here, even if you write f of nt, the independent variable is n only, not t. So independent variable is n, and usually we associate this with a time axis of the independent variable. That's why we call it discrete time signals. But the same theory is applicable, as I said, to a case, for example, if you are trying to find out the voltages at different nodes in a ladder network, then there is no time involved. The independent variable is the index of the node. Then again, we still, the same techniques that we adopt for discrete time signal processing can also be used there. Okay. Now, after having said this, then we would like to know what is meant by a discrete time system. Again, this is something which we already discussed, but let me review that. A discrete time system is one which processes discrete time signals. So we have, suppose we have single input, single output system, then the discrete time system will be represented by means of a rectangle like this, and the input may be x of n and the output will be y of n. So that is the input output relation. This is the input and this is the output, and this is the discrete time system. So as far as the single input, single output discrete time system is concerned, you let in a sequence of values constituting xn, and out comes another sequence of values which is yn. And this system therefore takes as input a sequence of values and produces as output another sequence of values. The relation between yn and xn is something which is of interest, which we will be discussing later. But we will be concerned with a particular class of discrete time system in our course here. This is the linear time invariant causal system. Discrete time system is what we are going to talk about in much the same manner as we have done in the case of continuous time systems. In the case of continuous time systems also, we talked about linear time invariant causal systems. Here also we are going to talk about linear time invariant causal systems. So before we proceed, let us once again review the meanings of these three adjectives. Linear, linearity. What is the implication of linearity as far as a discrete time system is concerned? We will say that if an input x1 of n gives rise to an output y1 of n, both are functions of n, and another input x2 of n gives rise to y2 of n, then if the system is linear, if c1 x1 of n, a linear combination of these two input signals, will produce an output which is the same form of linear combination of the output quantities for all constants C1 and C2. So if you take any two constants C1 and C2, provided this particular relation is satisfied, then we say it's a linear system. If not, it's a non-linear system. So much the same way as we defined in the case of continuous systems, except that in the case of continuous systems, you write x1t produce y1t, x2t y2t, and c1x1t plus c2x2t produces c1y1t plus c2y2t. Exactly the same, except that now we couch this in expressions which are relevant to discrete time signals. Then time invariance. What is the connotation of time invariance as far as this system is concerned? If x1n produces an output y1n, then if the system is time invariant, if you delay this x1n or shift it by a certain amount of time, in the case of continuous time we said tau, but in this case we have to delay it by an integral number of sampling instants. Therefore, you can say then x1 n minus m, where m is an integer again. That means the same signal is delayed by m instants of n sampling instants. Then the output will be a correspondingly delayed output quantity. Instead of y1 of n, we have y1 of n minus m for all m, for all integral m. It goes without saying that whenever we have an argument here, as far as the discrete time systems are concerned, the argument of must be an integer. So m, it goes without saying that m is an integer. In other words, if I have this is x1 of n, and that produces an output, say like that, this is y1, then if I delay this by m sampling instants, that is, instead of starting from 0, if I start this from m, then the y1 also will correspondingly get delayed by this instant. This is m. So it will be like this. So if you delay this input, this is x1n, this will be x1 of n minus m. And y1, this is y1 of n, this is y1 of n minus m. So this will be the result. That means the same set of samples, same sequence of samples will arise, but then it will be delayed. It will start from, if this is increasing like this will also increase like this. That is the time invariance. Thirdly, causal system. What is meant by causal system? The causal system essentially means if x1n produces y1n and x2n produces y2n. Furthermore, x1n equals x2n for n less than or equal to m. That means we have two signals which are identical up to mth sampling instant. Then a system is causal. We can say that y1n is also equal to y2n for n less than or equal to m. What it means is, suppose I have two signals. This is say x1 n. Up to mth sampling instant, it is how it is. Let us take x2n, which is also this, has the same behavior up to this point, but then later on it may differ. So this is x2n. So if these two are the input signals, x1n and x2n are identical up to the mth sampling instant, then we can say that whatever output this produces, let us say up to m, and then beyond that maybe like this, this will also have the same output up to this point, and afterwards it may be different. So up to this it is the same. This is y1n, this is y2n. So these two up to that point they are identical. They must be identical. This is the meaning of a causal system. For a linear causal system, we have a special result. if linearity is also implied, then it means if xn produces yn and xn is 0, say for n less than 0, then yn is also 0 for n less than 0. That is the meaning of causality for the special case of a linear causal system. That is, you are applying an input xn which is 0 for n less than 0. Then the output must also be 0 as long as the input is not applied. That means any output can come after the input is applied, not before that. All this is very similar to what we have discussed in the case of continuous systems. Now we have put these properties in terms of the notation applicable to discrete time signals. Now we will work out a few. Now we'll show a few equations pertaining to discrete time systems and show what are the implications as far as these equations are concerned that arise as a by virtue of the property of linearity, time invariance, and causality. Let us now look at these examples. So this is a representation of a discrete time system. It takes a sequence of values as input and produces the corresponding output. A digital computer, for example, can be thought of as a discrete time system. A digital filter is one such. So for a linear time invariant and causal discrete time system, there will be a linear difference equation connecting the output quantity y of n with the input quantity of x of n. An example of such a linear difference equation will be something like this: yn plus 2 plus a1 yn plus 1 plus a2 yn equals b0 xn plus 2, say b1 xn plus 1 plus b2 xn. So the input sequence of values xn are related to the output sequence in this fashion. This is something like your differential equation, except that we don't have derivatives here, but instead of that the argument is stepped up by 1 unit. Now this is said to be a second order difference equation. It is said to be the second order because the difference between the arguments, the highest argument of the independent variable, which is n plus 2, and the lowest argument of the independent variable is n, the difference between these two is 2, therefore this is said to be a second order difference equation. So this is a second order linear difference equation. So in contrast to a differential equation, we have what is called a difference equation, which governs the operation of a discrete time system. Further, the coefficients that are involved, a1, a2, b1, b1, b0, are constants, and that accounts for its time invariant character. So this is a constant parameter system. Which is the same thing as saying that is a time invariant system. We will see examples where it fails to be a constant parameter system. So in a linear second order difference equation will be of this type. You can also put this alternately by stepping down the argument by 2 units. You can write this as yn plus a1 yn minus 1 plus a2 yn minus 2 equals b0 xn plus b1 xn minus 1 plus b2 xn minus 2. This is an alternative form. So a second order difference equation pertaining to a linear time invariant causal system could be either in this form or this form, both are equivalent. By stepping up this n by 2, you get this. By stepping down by 2, you get this. Both are equivalent. In general, we can say yn is obtained as minus a k y n minus k, k from 1 to say n, plus b k x n minus k, k ranging from 1 to n. So this is, you can even have another value m index also, doesn't matter. So this is a general equation. That means I can write this, for example, in this first particular case, yn plus 2 as minus a1 yn plus 1 minus a2 yn, and like that. Similarly here yn I can write this as minus a1 yn minus 1 minus a2 yn minus 2 plus b0 xn plus b1 xn minus 1 plus b2 xn by 2. So when you shift all the, except keeping yn on one side and take all the other values of the output on the other side, you get this. So this is a general equation of nth order. So this is a general form of linear difference equation with constant coefficients of nth order. Now you can see now that this output sample yn at any point of time can be recursively calculated from knowing the previous output values, previous n output values, 1 to n, yn minus 1, yn minus 2. If you know all the previous output values up to n sampling instance earlier, and here the present input when k is 0, it is b0 xn, k is 1, b1 xn minus 1. That means any output at any sampling instant n can be computed from knowing the present input and the past m inputs plus the past n output quantities. So this is a kind of recursive relation which enables us to calculate yn from knowing the past outputs and the present input and the past inputs. In this form you can one can find it. One can, if you know the input quantities, successively you can calculate the output quantities. You can put this in the alternative form by shifting this on the other side. You get this in the standard form as shown here. Now let us consider some examples of difference equations which may or may not be linear, which may or not belong to time invariant discrete systems, but just to bring out the difference between the various types of systems. Examples. Suppose I have yn equals 6 x squared n minus 2. Now here this does not belong to this standard form, whereas in this standard form you have y's and x's only, no square terms are appearing, no products, either the input or the output quantities. So if xn is the input and yn is the output, you got x square here. This fails to be linear. This is a non-linear situation. Why it is non-linear? Suppose I have an x1n, then it gives rise to an output which is 6 x1 squared n minus 2. That's what you get. Let us say this is y1 of n. Now let me say if I multiply, if the input is doubled, let us say I have 2x1 of n, then if the system is linear I must get double the output. But what you get here is, since the input 2x1 of n, the output will be 6 times 2x1 n minus 2 whole squared, because it's x squared of n minus 2. So this becomes 24 x1 squared n minus 2, which is not equal to, because the input is doubled, we expect the output also to be doubled. This is 4 times actually, it is not 2 times, it is not equal to 2. This is y2 of n, which is not equal to 2 times y1 of n. So this is non-linear. So in a non-linear situation, we will not have this linearity, these terms. In a linear system we should have all these terms, both the independent variables, independent variables, and the dependent variables, all the terms must be of power 1. Square term spoils this. Second example. We have n cubed yn equals 6xn minus 2. Now, no doubt yn and xn, they don't have square terms or cube terms, so this appears to be linear, but then the coefficient of yn is n cubed instead of a constant. Therefore, we expect that this is not a time invariant system. So this is a variable parameter system because the coefficient of yn is not a constant, it is n cubed. This is a variable parameter, so time variable, not time invariant. We may say this is a variable parameter system. However, the system is linear. You recall that in the case of continuous systems, we said continuous time systems, we said as long as the coefficients of the independent variable or the dependent variable are functions of t, then still it is a linear system. Here also it's a linear system. Example, suppose x1n gives rise to an output which will be, after all, from this we know the output will be 6 of x1n minus 2 divided by n cubed. That is your output y1 of n. So n cubed times y1 of n should be 6 times x1 of n minus 2. Therefore, if x1n is the input, the output will be 6x1n minus 2 by n cubed. Suppose I have x2 of n is a new input, you will get naturally 6x2 of n minus 2 divided by n cubed, that will be y2 of n. Then it can easily be shown that if I have a linear combination c1x1 of n plus c2 x2 of n, where c1 and c2 are constants, then the output will be 6 times c1 x1 of n minus 2 plus c2 x2 n minus 2 by n cubed. That will be the output, which is indeed can be shown to be c1 y1 of n plus c2 y2 of n. So this satisfies the requirement of a linearity. Therefore, this system is linear, but it is a variable parameter system. So a variable parameter system obviously will not satisfy the property that if you shift the input by a certain amount, the output will not also be shifted by a corresponding amount. To illustrate this, let us consider yn is 3n times xn. This is again time variable system because the coefficient is a function of n. Let us see. Suppose I have x1 of n and it gives rise to an output which is 3n times x1 of n. This is your output y1 of n. Now suppose I take a x2 of n, a new input, which is the old input delayed by m sampling instance. x2 of n, which is the same x1 of n but delayed by n sampling instance. So this obviously produces an output which is 3n times x2 of n, which is 3n times x1 of n minus m. That's what we are having, and this is your y2 of n. This is your y1 of n. Now y1 of n minus m, if you want to see what y1 of n minus m is, this is y1 of m is 3n times x1 of m. So y1 of n minus m will be 3 times n minus m times x1 n minus m, and that is different from this. This is not equal to y2 of m. So the conclusion is that whenever you have the coefficients of x and y terms as functions of n, then it is a linear system, time variable system, but it does not satisfy the property that we are looking for, that when you delay the input by a certain amount, the output will also be delayed by the same amount. That property is no longer valid. Fourth example, suppose I have yn equals 3xn minus 2xn minus 1. So this is obviously satisfies all our requirements. It is all the parameters are the coefficients are constants, and this form pertains to the form that we have been talking about. This is a linear time invariant, and it will also be a causal system. The requirement of a causal system we will talk about in a moment, so we can take it that is a causal system. So this is the type of system that we are going to talk about, and there is no difficulty as far as this is concerned. Now let us take one more example where the system fails to be causal. Suppose I take yn as 3xn minus 1 plus xn plus 1. Now you see, an output at the nth sampling instant is dependent on an input that has occurred one sampling instant earlier plus an input that is going to occur later, n plus 1. So the present output depends upon a future input, right? So if there is an input here that has influenced the output even before the input has occurred, therefore this certainly is a non-causal system. So how do we recognize a non-causal system? The highest index that we have got associated with the dependent variable, that should not be exceeded by the variable that the index, the argument of the independent variable. Like you see here in the recursive relation, in this set of terms, the highest argument as far as the dependent variable is concerned is n, because all the others are n minus 1, n minus 2. The highest variable that you have, the highest value of the argument for the independent variable is also n, k equals 0, n. So that is why this is a causal system. If you started k equals minus 1, then it becomes n plus 1, then that fails to be causal. So since we are talking about the output, it depends on the present input and the past inputs, not on a future input. Here we have a case where the output depends upon a future input, therefore it fails to be causal. To show this more explicitly, suppose I have two inputs x1n and x2n, both are equal for n less than or equal to m, and x1n is not equal to x2n for n greater than m. Suppose I have two inputs, and let us find out the outputs of these with respect with the inputs x1 and x2 at the nth sampling instant. Therefore y1 is the output corresponding to x1. I want to find this output at the nth sampling instant, y1 of m, with this input x1 of m. Therefore according to this, y1 of m will be 3 times x1 of m minus 1 plus x1 of m plus 1. y2m, the output corresponding to the input x2n would be 3 times x2 m minus 1 plus x2 m plus 1. So we have two inputs which are identical up to the mth sampling instant. We would expect the outputs also to be identical up to the mth sampling instant, capital M. But when you compare y1 of m and y2m, are these equal? If you look at this, this is equal to this because x1 equal to xn up to n equals m. But x1 m plus 1, there is no necessity for this to be equal to x2 m plus 1 because these two are equal only up to n equals m. These two may not be equal. this and this may not be equal. So y1 of m, there is no guarantee, is not equal to y1 of m is not equal to y2 of m. Therefore, even though the inputs have remained the same up to the mth sampling instant, the outputs are not equal. Therefore, this is not a causal system. The final conclusion from this is the argument, the highest argument associated with the dependent variable, whatever it is, the highest argument associated with the independent variable should not exceed that. Here n plus 1 is exceeding n, therefore, this is not a causal system. So after having considered the various types of systems and the pertaining equations, we will now have a look at the standard signals, discrete time signals, which we will make use of in considering the performance of discrete time systems. Now let us look at the basic discrete time signals. The first signal that we will talk about, the unit impulse. It is also called unit signal or unit sample. Basically, so it is 0 everywhere except when n equals 0. So this is called delta n, that is the symbol that is used for this. It's equal to 1 for n equals 0 for n not equal to 0. So this is just a single sample occurring at n equals 0. This is called a unit impulse, simply called a unit sample or a unit signal. It is the term impulse is used borrowing the terminology from the continuous time signal. It does not mean the value of this at n equals 0 is infinite, it's finite, it is equal to 1. So impulse perhaps is a kind of misnomer, but still we will call it a unit impulse because it corresponds to what we have as a unit impulse in the continuous time system. It is symbolized as delta n, 1 for n equals 0, 0 for n not equal to 0. Now, just like a unit step, we also here are in the continuous case, here also we have a unit step symbolized as un. Now here the value of this discrete time signal is 1 right through for all non-negative n, 0, 1, 2, etc., and 0 for negative values of n, like that. So un can be written as 1 for n greater than or equal to 0, 0 for n less than 0. So in contrast to the continuous time case, here at n equals 0 we have a definite value which is equal to 1. In the case of a continuous time case, at t equals 0, as a unit step is concerned, we can take it as 0 or 1 or half or whatever it is. It can be left ambiguous. But as far as the unit step in a discrete time case is concerned, the value is definite and is equal to 1. So this value is equal to 1. Here also this is equal to 1. Now similarly, you can have a unit ramp. It is symbolized as Rn equals n for n greater than or equal to 0, 0 for negative values of n. So that would be 0 everywhere, but here it will be 0 like this, 1, 2, 3, 4, etc. up to. So at 1 it is equal to 1, at 2 it is equal to 2, and so on and so forth. So that is what is called a unit ramp, which is somewhat similar to what we have in the case of continuous time system, except in the continuous time as a function of t it takes off like this, but here the values of the samples increase in proportion to n. We can also have an exponential signal. E to the power of alpha n. So you have something like the exponentially increasing. like this, e to the power of alpha n. Now on the other hand, if I have e to the power of alpha n times u of n, that means this is multiplied by a unit step, that means all the samples are cut off and you are having only this portion. That is obvious. If you multiply e to the power of alpha n by un, that means the negative samples for negative values of n are just removed. They will be equal to 0, of course. Similarly, you can have a sinusoid. You can have sin omega, n omega n or n omega, which will be, in a general case, this is the envelope, the samples will be like this, all the samples will fall on an envelope which is a sine wave. Similarly, if you have cos n omega, it will be a similar situation, but this will be now a cosine term. So the samples will be again discrete, but the tips of all the samples will follow a sine wave or a cosine wave as the case may be. Sine omega n omega or omega n, can write maybe better call it n omega, sine n omega and cos n omega are sinusoidal signals. Again, if you take sine n omega multiplied by u of n, this portion will be cut off. Cos n omega multiplied by u of n, this portion will be cut off. Now these are the basic type of discrete time signals that we would like to use. From this we can build up other signals, for example e to the power of alpha n, sin n omega, that type of signals, multiplication of these two, all those things can be produced. Now after having considered the difference equations, we would like to find out what are the methods of solution for the difference equations. So methods of solution in time domain, methods of solution of difference equations in time domain. We will talk about, first of all, classical method of solution of difference equations. Classical method of solution of difference equations. Secondly, we can have very elementary procedure, step-by-step procedure. Using a recursive relation, step-by-step procedure. The third method would be the Z transform method. These are the three methods that we are going to discuss. The classical difference equation solution will have a technique which is corresponding to the solution of differential equations that you are familiar with. The second method is step-by-step. Numerical calculation is convenient because you have a recursive relation from the values which are known at the present instant of time. You can calculate the value of the dependent variable at the next sampling instant and so on. Proceed step-by-step. The Z transform method corresponds to your Laplace transform technique, and we'll spend a lot of time on this. As far as the first two methods are concerned, we'll briefly discuss these methods in the next lecture, how to go about solving the difference equation. We'll consider a very cursory treatment we'll have as far as these two, first one is concerned. We'll illustrate the step-by-step procedure, nothing much to be said about it further, and later on we'll talk about the Z transform method. That the first two methods we will take up in the next lecture. So in this lecture we have introduced ourselves to the concept of discrete time signals. We mentioned discrete time signals are those which are defined for discrete values of the independent variable. Usually it is time, that's why it's called discrete time signal. It could be any other independent variable like a space coordinate, the values of, for example, heights at different points along a line. Now we indicated a discrete time signal as f as a function of the independent variable n, fn, xn, yn as the case may be. We can also write y subscript n if you like that. That is also an alternative way of doing that. And we also discuss the difference between a digital signal and discrete time signal. A digital signal is one which is a discrete time signal also, but the amplitudes, the values of the signal is also quantized, is allowed to take only discrete, well-defined values, not any value in between. Then we talked about a discrete time system, which is one which processes the discrete time signals. We talked about the linearity property, the time invariance property, and the causality property, and we will confine our discussion to linear, time invariant, causal discrete time systems. These are characterized by a difference equation of order n in general, where the order of a difference equation is the difference in the arguments corresponding in the highest argument and the lowest argument associated with the dependent variable. We worked out some examples where these attributes of linearity, causality, and time invariance fail, and we can, from looking at the equation, we should be able to tell whether these attributes hold or not. That we worked out some examples to illustrate this. Then finally, we said the solution for this, we looked at the basic forms of discrete time signals. We defined the impulse function, the unit step function, and we saw how a discrete time sinusoid and how discrete time exponential functions look like. Then we said the methods of solution of the difference equations pertaining to these systems. We will talk about three methods. One is the approach of the classical difference equation solutions. Then the second is step-by-step method, and the third is the Z-transform method. We will discuss the first two methods in the next lecture, and later on we will take up the Z-transform approach to the solution of difference equations.